Now we're going to talk about decomposition reactions. Decomposition reactions fall into several different categories. Let's start with the simple decomposition reaction here. We have just a compound that's maybe it's being heated or electricity is being pushed through it. That's one of the first things that was done for decomposition reactions historically, is you would take this compound and you would zap it with a lot of electricity, and the compound just falls apart, breaks apart into its pieces. So the pieces for calcium chloride. Calcium chloride. What are the two pieces to calcium chloride? Calcium and chlorine. And when we break them apart, we got to take them to their natural states of matter. Calcium's almost always a solid. Chlorine is a gas. Also, chlorine falls in that category of diatomics. How many diatomic molecules are there? 7. Right, there's 7. The Brinkelhoff, Hofbrinkel. Whatever you want to say, that would work. So what are those 7 diatomics again? They are, let's see, we have an argument between whether or not it's Hofbrinkel or Brinkelhoff. All sorts of different ideas. Here we have Hofbrinkel. Maybe you're a fan of Miss Hoffman. You want to say Hofbrinkel? Any of these elements that don't have a charge, and this chlorine here doesn't have a charge, they are what we call diatomics. So that by themselves, they're always in pairs of 2. So chlorine's by itself now, it's got to be diatomic. So let's go into some of the more difficult decompositions. Here's one. This decomposition reaction involves hydroxides. Anytime we have a hydroxide with a metal and it decomposes, the pattern is to make the metal pair up with an oxide and to make water. So let's think about this. Our metal in this example is calcium. What's going to be our first product then? CaO. We're going to take the calcium, that's the metal, and put it with one of the oxygens. And when we do that, we are going to worry about the charges. And calcium is a +2, oxygen's a -2. So this is the correct formula for that oxide that's being formed. We also are going to make water. After we put these together, we then need to worry about balancing the reaction. Now we're getting lucky in this example. We have 1 calcium, 2 oxygens. Here's an oxygen plus another oxygen, so there's 2. 2 hydrogens, and we have 2 hydrogens. So here's another one. This is a decomposition reaction for acids. These are ternary acids. Ternary means that there are 3 parts. Or you could think of it as hydrogen and some sort of polyatomic ion, like a sulfate or a phosphate or a nitrate, something like that. The first thing you do is you break that polyatomic ion apart and you make water, and then whatever is left other than the water forms that nonmetal oxide. So in our example here, we have H2SO4. We're going to pull off the water. Look at this. What haven't we used yet from the H2SO4? We haven't used a sulfur. And what else is still left? The O3. So we make water and some sort of nonmetal oxide. This can happen in a simple format like we have here. It could be a little bit more complicated than that, but for our purposes, that's where we're going to leave it. Let's do one more real quick practice one. Let's say that we had I'm already committed to, oh, that's horrible. That was just horrible. Let's just delete that. Try again. All right, let's try H2SO3. Again, we pull the water off, and this time we'd have sulfur dioxide left over. Sulfur dioxide is usually a gas. Water's a liquid unless this happens to be a very hot reaction. It's going to probably be a liquid. Here we go. Here's a carbonate. Decomposition reactions involving carbonate. We have the metal and the carbonate. and we're going to make a metal with oxide and carbon dioxide. So in our example, we have calcium carbonate. So the metal is calcium, and we're going to make calcium oxide. Again, when we do that, every time we do it, we need to think about the charges. Calcium's a +2, oxygen's a -2. So that appears to be the right formula. We'll do another example in a second where the charges are a little bit wacky and we have to think about it a little bit more than this example. The other product, again, would be carbon dioxide, and this reaction is already balanced. But that's a little bit too simple. Let's do one that's more difficult. Let's do aluminum carbonate, Al2 parentheses CO3 3. Our oxide would be with aluminum. What would be the formula? If we were making aluminum and oxygen, it would be Al2O3. Yes. Aluminum's a +3, oxygen's a -2, so Al2O3. And then we're going to make, what's the other product for carbonates? Yeah, carbon dioxide. Now this one's a little bit harder to balance. We have two aluminums. How many carbons are here? 3. Let's go over here and fix it with a 3. That's 3. So we have 6 oxygens plus 3 more is, and we have 9. So that one is now balanced. All right, so we have 2 more decompositions. Here's one with chlorates. Chlorate, there it is, chlorate. We have a metal and chlorate. We're going to make a metal chloride and oxygen. So we have our metal with chlorate. We're going to make a metal chloride, which would be Na and Cl together. Sodium is a +1. Chlorine is a -1. So those charges work fine together. Let's move that 2 out of the way for right now. And then we have to make oxygen as the other product. When we go to balance this afterwards, we have, let's see, how are we going to balance this one? Yeah, we got to try to make the oxygens even. That also affected the sodium chlorides. And I need a 3 in front of the oxygen, and that would be balanced. And the last example is just a simple decomposition involving oxygen. Take a metal oxide, break it apart into the metal and into oxygen. And just make sure you balance it afterwards. Remember, oxygen is one of those diatomics. That's kind of what makes this one a little bit difficult, but not too bad. Questions?